For chapter 16, we'll review 6 sections, and I'll try to save the lecture into 2 videos, 30 sections each. Let's go to the first section, line integrals. If f is defined on a smooth curve C, and C is given by this map, R of t has 2 components, so it is a plane curve. T is moving from A to B. Then the line integral of f along C is defined in this term. S is the arc length element. The right side is the limit of Riemann sums. Once a curve is given, then we may consider partition. And now for ith one, we can find the delta x and delta y. And with this right triangle, by using the Pythagorean theorem, we can approximate the arc length by using this length of hypotenuse. Okay, so delta SI is given in this way. Now, it can be written in this way. There's delta x over delta t squared plus now delta y over delta t squared and then delta t. When we take the limit, so delta t becomes smaller, 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 then now this one will approach to that one. So the line integral can be evaluated by using this formula. And in t domain from A to B, this quantity is the same as the length of R prime. For vector field, we can define line integral. The vector field is f is a continuous vector field defined on a smooth curve C by the representation. Then the line integral of the vector field along C is notated with that term. And in definition, we try to find the integrate only the tangential component of the vector field, so that is tangential component f dot t. T is the unit tangential vector. And that is same as, in fact, that is r prime over r prime length. And ds is the same as now r prime length dt, so that this one error will be cancelled, and then we reach this formula. That is for evaluation. Okay. Evaluate the line integral where C is the line segment from this to that point. Okay. When we try to use the evaluation formula, we have to parameterize the curve. Okay, that is line segment. So that is R of t is same as 1 minus t. Let's say there's point P, there is point Q, and P plus now T and Q. But P is 0, so that we have T times Q, which is 2t minus 2t and 1. Oh, that is t. Okay. For this one, this is a scalar function. For the scaling factor, it is r prime length. So let's try to get r prime. That's 2 minus 2 and 1. So that the length of r prime, that must be, okay, square 4. Again, square is 4 and square is 1. So it is a square root of 9 which is 3. Okay, we found the scaling factor is 3. So the given integral must be same as, of course, the t must be from 0 to 1. So that they're same as integral from 0 to 1. Now, that is x, 2t. Over there we have x. And e to the y squared, so 4 squared, minus z squared, that is t squared. And we have to have here scaling factor and dt. Right? So we have here from 0 to 1, 6t. And e to the 3t squared and dt. An antiderivative is quite easily obtained. There's e to the 3t squared. If you differentiate with respect to t, then 6t will come out. So we have 6t here. Now that is from 0 to 1. It's 1, then e to the 3 is 0, then e to the 0, which is 1. So that's the final answer. Okay. For now, the vector field, we'll try to get line integral. Vector field is given here, and it's moving particle along the parabola, that is curve, from 1, 0 to 2, 1. So the vector field integral must be work. Okay. Let's try to visualize the curve. X is y squared plus 1 must be given in this way. Now, that is 1. It is moving from 1, 0 to 2, 1. So that must be 2 is 1, and height is 1. Now, it's moving from here to there. So that is C, right? Okay. Now, we have to find the representation R of t for the curve. Once we choose t for y, then x is t squared plus 1. And y is moving from 0 to 1, so that t is in 0, 1 interval. From here, we can get f of r. That is, we have to express this vector field as a function of t. Okay, x is t squared plus 1. Now, y is t e to the t squared plus 1. So that is vector field as a function of t. And we have to have r prime. Okay, we are trying to use this formula. And f of r dot r prime and integral from a to b. Right? So you have to get r prime. That is 2t from this one and 1. So they are dot product. F of r dot r prime is okay. This multiplication will make 2t cubed and 2t, and that is t e to the t squared plus 1. So the line integral is from 0 to 1. T is moving from 0 to 1. Now that is the integrand. 2t cubed plus 2t plus t e to the t squared plus 1. Now dt. Okay. From the first one, 1/4 t to the 4. So that half t to the 4 plus t squared. And then for the last one, we have a scalar must be given, and that major part must be this one. Once it is differentiated, then that will make 2t and e to the t squared plus 1, so that we need here half. And we are evaluating from 0 to 1. From the first one, we have a half. From the second one, we have 1. And from the last one, we have a half is there. Once t is 1, then e squared. And once t is 0, then e to the 1, which is e. So we have this final answer. Okay. Let's move on to the next section. It is the fundamental theorem for line integral. This theorem can be used for either the plane curve or curve in the space, three-dimensional space. F is continuous, and the vector field is continuous and is conservative. That means there is potential little f such that the vector field can be written as the gradient of the potential. Then the line integral of the conservative vector field can be written in this way, and we can evaluate through the values of the potential at the terminal point, at the beginning point. This one, the line integral as independent path, means that only the beginning point and end point is the same, then independently of the path choices, the integral must be the same. Then in the case we say it is independent of a path. That is equivalent to this claim. The integral, line integral is 0 for every closed path. Once, if you choose closed path, then the integral must be 0. That is the same as now for arbitrary beginning and end points. So you can choose the various curves, paths, but the integral must be the same. So that is independent of a path. Okay. Now, once F is a vector field that is continuous on an open connected domain, and if this integral is independent path, then it is conservative. Once it is conservative, then independent of path. Now, this one is saying that along with some condition, once it is independent of path, then it is conservative. So basically, if you can choose open connected domain and the vector field is defined on open connected domain, then conservativeness and independence of path are the same. Now, once the vector field in the plane PQ is conservative, this vector field is conservative, and PQ have continuous partial derivatives, then we have that equation. Q sub x is same as P sub y. Now the domain is here simply connected domain. And then the equality, that equation implies conservativeness of F. So eventually, now domain is simply connected, then conservativeness and this equation are the same. So by using this equation, we can check if the given vector field is conservative. Once this equation is satisfied, then we can say it is conservative. roughly speaking, when the vector field having two components is smooth enough, then we can choose here simply connected domain. Conservativeness, independence of path, and the equation are equivalent. Okay, let's try to find work done by this force in moving an object from a point to another. That is the beginning point, that is the ending point. Okay, for this one, this is P, that is Q. So let's check if it is conservative. And you can do it quite easily. For Q, now x derivative, which is 3 times square root of y, P y derivative, then 2 times 3 over 2 y to the 1/2 power. So we recheck that one. So they are the same, which means that F is conservative. Then there is a potential F such that gradient of F is given vector field. The first component is F sub x. From this side, the first component is 2y to the 3 over 2. And second component from the left-hand side is F sub y. From the right-hand side, that is 3x square root of y. Okay. Now, we have to solve these two equations. Let's say there's 1 and 2 to find the potential. From 1, x integration will make 2x y 3 over 2. And you will have to put here constant, but we have to put it quite general, such that x derivative will make it 0. So this constant must be a function of y. Okay. Now we have to find this term. So from here, we make derivative, y derivative. Then now we put out. So it changes the 3 and x and y. That one must be y half power plus g prime y. Now we compare this one with the second equation. Then these two terms are the same. So that means g prime y must be 0 as a function of y. Now its derivative is 0, which means that g must be a real constant. So we conclude here the potential F is 2x from here and y 3 over 2 plus a constant. So the work is a line integral, which can be found from the potential. Now, potential endpoint is 2 and 4, and beginning point is here 1 and 1. So ignoring the constant F24, that is 2 times 2, and it's 4 to the 3 over 2, which must be 8 minus 1 and 1, then 2 times 1 and 1. So that is a 32 minus 2, which is 30. Okay? So we found the work. Vector field is given in this complicated way. Find the potential, which means that this is conservative. You can check it quite easily. From this one, for Q, you make x derivative. From here, you make y derivative. Then you'll see they are the same. Anyway, once it is conservative, then we have potential. The gradient of F must be the vector field. That means now again F sub x is the first component, e to the y plus y cosine x f sub y equal the second component x e to the y and sine x, right? So exactly the same manner we can get it. First, from the first equation, we try to make x integration. Then f is, okay, e to the y is a constant, so the x e to the y, and x integration, that means y sine x, right? And plus g of y, so that x derivative will make it 0. Okay, now we have to decide this one. In order to do that, from here we make y derivative. Then there is x e to the y, and y will disappear, and sine x, and that must be g prime y. We compare this term with that second equation. Then this portion is the same as okay, this one, so that g prime y must be 0, which means that g is a real constant k. So we found here f, the potential, is from here x times e to the y and plus y sine x and a constant k. Right? Okay. So to get the integral, evaluate the integral, now we have to use the beginning point of the curve and end point of the curve. Because it is independent of path, you are taking only beginning point and end point. Okay, so that is R0 is beginning point, t is 0. Okay, then that is 1, and second component must be 0. Okay, we have to put this way. And then R pi, then e to the pi, cosine pi is minus 1, so that the first value is minus e to the pi, and pi then is 0. Okay, so the answer, the given integral must be f of minus e to the pi and 0 minus f of 1 and 0, right? Okay. Now, x is minus e to the pi and y is 0. Then from this on, we have minus e to the pi. And now y is 0, so that will be 0. From this on, we have that. And minus x is 1, y equals 0. X is 1, y equals 0. So it is 1. X is 1, y equals 0. Again, that is 0. And we ignore k. Then we have here minus e to the pi minus 1. That's the final answer. Okay. Now we'll go to the Green theorem. Okay. Now, if we consider positive oriented curve, but that is simple closed curve, then D is a region bounded by the curve, so inside. So the curve is defined in this way. There's positively oriented, and okay, that's C, then inside is D. That direction is negatively oriented. Once you walk along the curve, then you can see the region left hand side. Then it is positively oriented. F is a two-dimensional vector field and has continuous partial derivatives. Then the vector field integration, line integral of vector field, that is obtained through this area integral q sub x minus b sub y along over the area. So that is Green theorem. And once we choose here the quantity is 1, then that will be area. So we can choose P and Q such that, or vector field, such that the quantity Q sub x minus P sub y equal 1. That is, for example, now Q is x and P is 0, then we have 1. So that is one example. Then this one can be written as the area formula. And this is the other choice, and average is obtained in this way. So that is an application of the Green theorem for the computation of area. Along the boundary, we try to integrate x dy, then you can find the area once the curve is closed. Okay. Now here, we'll try to solve this problem. Now, this line integral, f is given in this way, and c is a circle with this one and oriented clockwise. Okay, let's see the curve. And center is 0, x is 0, y is 1, and radius 1. So that it is given in this way. That is 1. And now clockwise orientation. So it is negatively oriented. So the given integral must be negative of the area integral. So inside is d, and curve C is given in this way. So we need this negation. And here the integrand is q sub x minus p sub y and dA. Okay, that is same as minus double integral over the, let's see, now q sub x derivative for this one, x derivative is, okay, there's 2x and plus 2y minus now p sub y, y derivative, which is 2y. Okay, so that is same as 2y will disappear, minus integral over the 2x dA. Right? Now, for that one, we have to have a strategy to get the integral. This is a polar region. Angle is moving from 0 to pi. Now, r is moving from here to there, like that. So we have to find the polar equation for this one. Now, we start with x squared. The equation is x squared plus y minus 1 squared equal 1. From here, now x squared plus y squared minus 2y plus 1 equals 1. We can cancel this one so that we have here x squared plus y squared equal 2y. In polar coordinates, the left hand side is r squared, right hand side is 2, y is r sine theta. So we can cancel r. The r is 2 sine theta. In polar equation, the r is 2 sine theta. Okay. So angle is from 0 to pi. R is from origin to over there. So 0 to 2 sine theta. And then, oh yeah, we have a minus here. And 2 times x is r cosine theta, right? And then we have to have r, one more component. We have to have r here, and dr d theta. Right? Okay. Now, for this one, we may put, okay, there's r integration first. So that is 2r squared. So 2 can go out. So the minus 2 from 0 to pi. And cosine theta maybe go out here. And then, okay, the remainder part is r squared, which is 1/3 r cubed. R is moving from 0 to 2 sine theta. And we have the theta here. Right? Okay. Now, from this one, okay, let's try to simplify. If we evaluated that one, then 1/3, and we have 8, okay, 8 sine cubed theta, right? So we can put this one again in front of that. So that is now minus 3 bottom, and that is 16 from 0 to pi, and cosine theta and sine cubed theta d theta. Right? Okay. From here, now minus 16 over 3, and antiderivative of this one, okay, it's simple. That is 1/4 of sine 4th power of theta. Okay, 0 to pi. Now, when theta is 0, the value is 0. When theta is pi, again 0. So that is completely 0. Okay, so 0 is the final answer. Okay. Now, as an application, we can use the Green theorem, and area of the region can be obtained by using this line integral, and along each boundary portion, and we have to sum after getting the solution, and each one we have to get here x dy integration. So for each line segment, for this example, you have to parameterize, and you have to get this quantity, and later on you can sum. Okay, let's begin from this one. We want to get the area of this region. Now, for along this portion, there's no change in y, so that the integral x dy here must be 0. Now again, that is change in y is 0, so that must be 0. Now x value is 0 along this one, but y is changing from 2 to 0, so change in y is minus 2, but x value is 0, so that no contribution. Only from here you can get non-trivial value. In fact, area of this region is 6, so that line integral along this line segment must be 6. Let's check it. Okay, beginning point is x is 4, y is 0, end point is now 2 and 2. So you can make parameterization out of t. That is 1 minus t beginning point, 4, 0, and endpoint t times the endpoint 2 and 2. That one must be here. The first one must be 4 and okay plus okay, in fact, okay, that is, let's try to write one more time. Okay, that is from here, that is 4 and 0, and along with this t, and that's plus t, subtraction, there's a minus 2 and 2. This one minus that one, and minus 2 and 2. So that is the first component is 4 minus 2t, second component is 2t. Okay, and t is moving from 0 to 1. So here for this one to second one, integral c to x dy must be, now from 0 to 1, x is 4 minus 2t, and there's y prime, which is 2, and dt. So we have 2 times, okay, now antiderivative for that is 4t minus t squared from 0 to 1. So that is 2 times, that is 4 minus 1. So we have a 6. Okay, so from this portion, the line integral is 6, 0, 6, 0, 0. The addition is 6, right? Okay, we'll continue in the second part. Thank you.